So it's a pleasure to have Christoph Dorn talking with us about transversal stratifications.
Yes, thank you very much, Chris. Can everyone hear me all right? Yeah, great, fantastic. So yes, I want to talk about the topic of transversal stratifications, and everything I have to say about this topic today is joint work with Chris Douglas. Unfortunately, I can't give a reference to a written up version yet. I was hoping we would complete this in time for this talk, but now it's almost finished, and it should be on the archive very soon. So before I give any technical details on transversal stratifications, I wanted to give a pictorial illustration of one of the questions that actually motivated this line of research. Namely, very vaguely speaking, we're thinking about finding a unifying definition for certain geometric structures that were popping up, for instance, in singularity theory, in higher category theory, and related areas such as TQFTs. But let me be a little bit less vague and show you some actual pictures. So I want to ask the question whether there's a geometric structure that captures in general dimension pictures such as, for instance, the braid, the Hoff map, or similar representations of maps, the pair of pens, maybe with defects, or the cusp or other singularities from singularity theory. And maybe the first thing worth pointing out is that, so these pictures are not just meant to be understood as cobordisms or tangles or stratified versions thereof, because really when someone draws these pictures, they really intend that there's also some notion of direction in this picture, which for instance means that the braid is not something non-trivial, but there's a change of relative position with respect to this direction from left to right of the two strands. So it's not to be understood as an identity cobordism. And similarly, for instance, for the cusp, where it matters that in the line on top, this line actually changes direction with respect to this direction from left to right in this picture. So this is actually a non-trivial question in the pictures that I've drawn, which can all be embedded in R3. It's a question that has been addressed. So dimensions 2 and 3 of string and surface diagrams are things that have been formalized. But really, we were trying to understand these things in general dimension. And transversal stratifications are a structure that achieves such an understanding. Now, this might be not super surprising to you. After all, these pictures are all very geometric, so there should be some geometric structure capturing them. So I hope that you'll be a little bit more surprised by this next question. Namely, we were in particular interested in trying to understand an algebraic structure which could potentially underpin these geometric objects. So we were asking whether the structure of transversal stratifications actually has a finite algebraic or combinatorial counterpart. And this is what this talk is really going to be about. So the answer to this question is yes, and it's nice. And yes, so the talk is going to focus both on the transversal stratifications part, but also on this underlying algebraic structure. Let me give an outline of the ideas, just to organize the order of topics a little bit in the talk. So certainly, given that title has stratifications in it, we're going to talk a little bit about stratifications, which are certain decomposition of spaces as indicated in the picture. But then very quickly, we're going to go to something which has additional structure. Namely, there's going to be some structure like a foliation on the stratification, and we're going to require transversality conditions between the strata, between the subspaces of this decomposition and the foliation. And really, we are going to be interested in the local case where the foliations are just standard foliations, which is shown on the picture on the right here. So this is going to be the second part of this talk, and then in third part, we're actually going to talk about the combinatorial classification. And I want to give you an idea of how this is going to work. So this is going to be a two-step process. So first of all, we're going to find that there's a specific sense in which these stratifications, these transversal stratifications can be triangulated. They can be triangulated, they can be triangulated into a structure which looks very similar, but is substantially easier. So this is actually an illustration of a triangulation of this picture on top. And they're simpler in the sense that, for instance, in the sense that all the strata and the stratifications are actually homomorphic to disks. And these structures, which are going to be called disk stratifications, are then going to be equivalent almost immediately by passing to the entrance path posets in a certain way, which is combinatorial structure, which you can associate to each stratification, as we'll see. And these disk stratifications will be so simple that you can fully recover the information from the entrance path posets, which are actually going to be a little bit more complicated than just posets. They're going to be chains of maps of posets. And then the last piece of the puzzle for this combinatorial classification is going to be something that I'll refer to as Hauptvermutung. Because really, it's not only the case that you can triangulate these transversal stratifications, but you can also triangulate them in a unique, simplest way. So the classical Hauptvermutung tells you that if you have two triangulations, you can always find a finer one. Here, the situation is somewhat the opposite. So we can always find a unique coarsest, a unique simplest triangulation of these transversal stratifications. And putting these two pieces together, or actually these three pieces, will then give us the combinatorial classification. And if we have time, there are going to be some immediate applications of this. So one I mentioned in the abstract. So all of this is somewhat morally also connected to more surf theory and singularity theory. So we'll be able to stratify the space of tangles with an interesting stratification that is strongly inspired from more surf-theoretic ideas. Okay, but the first thing that's on our to-do list is number one. So let's start with an overview of the relevant concepts from the theory of stratifications. And first and foremost, I wanted to start with the definition of a stratification, because there are actually, well, many different definitions for stratifications, but we're going to work with a particularly simple one, which is simply, so stratification F on X is simply disjoint decomposition of X into connected subspaces, X subscript S, which are also going to be called strata. And this decomposition satisfies a condition which is called acyclicity, which translates into the acyclicity of a certain graph. So we require the decomposition to acyclic. And this means that the graph GF associated to our stratification F, whose edges are given between between 2 points, and I should say the points of this graph are simply the indexing set of the stratification of the decomposition, and edges are given if and only if the closure of the first stratum intersects the second stratum non-trivially. So let's unwind this a little bit. So let's unwind both what this acyclicity really means, and let's unwind what this non-trivial intersection condition means. Namely, under some light path connectedness assumptions, you can write this in a much more readable way. So under some light assumptions, this intersection condition holds if and only if there's a path which starts in the stratum XS and lives for almost its entire life in XS, but ends in XR. And such a path is going to be an example of what we're going to define in a second to be an entrance path. Okay, let me now tell you what this acyclicity really means. So a graph which is acyclic has a, well, every graph has a transitive closure, but it's a poset precisely if the graph is acyclic. So just as we called this path an entrance path, we can now define this transitive closure of the graph to be the entrance path poset. And that's usually denoted by enter F. One thing to note is, well, there's almost immediately a map from X to this poset, which simply takes a point in the stratum XS and maps it to the corresponding object of the entrance path poset. And for people who are, for instance, familiar with the definition of P stratifications by Lurie, this will be a point of connection. So this map, of course, is continuous with the appropriate specialization topology on this poset. But really, we don't even need to know that for the next definition, which now defines a general entrance path to be a path in our total space X, so in our underlying topological space X of the stratification, such that when you post-compose with this map to the entrance path poset, you actually get a monotone map from the ordered interval to the entrance path poset. All right.
Hey, Christoph, this is David Ayala. If you could just say a word on the path-connected assumptions, just to give me a flavor of what those assumptions are, I'd appreciate that.
Yeah. So for really only this thing to be true, what you need is that the union. So if this condition holds, then the union of XS and XR should be path connected. For instance, you can also, yeah, that's one condition. That's essentially a very trivial condition for this to hold. Yeah.
Okay.
Okay, so this entrance path poset, for people familiar with stratifications, it will be clear, but this entrance path poset is really a truncated version of something that potentially has higher structures. So this entrance path poset should have higher structure. Namely, in a similar vein of defining entrance path, we can also define entrance homotopies, entrance higher homotopies to be just again homotopies or higher homotopies. But whenever we fix all but one variable of the homotopy, we require this to be again inducing a monotone map. So in each variable, we require an entrance homotopy to be an entrance path. So here's a small illustration. So if you have a family of entrance paths, then what you require is that if you fix a parameter of this path, then the path that you get from the parameter that describes the entire family should also be an entrance path. Now that's just a sketch, I should say. So it's not really something that leads to a precise definition. What does lead to a precise definition is when you consider conical stratifications, which we are going to actually meet in a different form at the later stage in this talk. So for this specific type of stratifications, you can define an infinity category of entrance paths. And there are, for instance, definitions by Lurie, but also by David Ayala and John Francis, and these are equivalent. And I wanted to illustrate this again with a picture and an actual stratification. So these gray parts in the back should be understood as a stratified space, as a decomposition of a space, and then a higher entrance path or an entrance homotopy between two paths could, for instance, look something like this. At the same time, what I've drawn would also be, in fact, a two simplex in this infinity category of entrance path. The entrance path, the higher entrance path category is one way to generalize the fundamental infinity report of a space to the setting of stratified spaces. But there might actually be other ways. So I wanted to compare this to an idea which John Baez had in 2006 of higher generic paths. So John Baez was thinking about paths which would be generic in the sense that if you perturb them just a little bit, they essentially look the same. So in particular, they pass through the same strata. And I've drawn only generic paths, but of course, this would be a non-generic path because a small perturbation would lead to a path that, vaguely speaking, looks different. Now, if you just write down a higher category like this, it wouldn't be a very interesting category because, of course, almost all higher homotopies are generic, more or less by definition of genericness. So you would really only recover the homotopy type of the underlying space, which is not super interesting, but I still think that John Baez probably had his reasons for considering this category, and I want to use it as a foreshadowing of what we are going to see at a later point, namely this genericness really translates quite nicely into the transversality condition that we're going to see later on. And really what's missing to make this rough idea precise is a more rigid structure on the collection of generic paths so that you actually get, so that you can meaningfully restrict them and get something that's not just the homotopy type of the underlying space. Okay, but all of this was really a tangent just to talk about this idea which John Baez had 2006 already. There's still a couple of things for stratifications that I want to mention. So we've seen what stratifications are. They're just these decomposition of spaces, and we've seen a notion of entrance paths and the entrance path poset. Stratifications also have maps. A map of stratification, this is the slogan, is simply a map of the underlying topological space that maps strata into strata. So in particular, what it cannot do, it cannot take a stratum and spread it out across multiple strata. It's quite straightforward to make this precise. So a map of stratifications is simply a map of the underlying topological spaces which descends along the canonical maps to the entrance path posets to a map of posets of the entrance path posets. Let's look at some examples of this. So here I've drawn two stratifications and a map between them, which should be understood as a sideways projection. So really I want to map these two strata onto this stratum, and I want to map these two strata onto this stratum. This is a perfectly fine map of stratifications, as you would be able to verify with this definition. What would not be a perfectly fine map of stratifications would be if you decide to map an entire wedge onto the point and then the other wedge in one way or the other onto this line, because then you would split up the stratum and map it across two strata, which would not descend to a map on entrance path posets. Here's a second example of stratified spaces. And in this case, the underlying map is really just the identity. So the underlying map is supposed to be the identity in this example. And in such a situation where the map is identity or homeomorphism, the only thing that can happen is that you can take strata in the domain and you can group them together into a potentially bigger stratum in the codomain. Or if you look at it in reverse, what you can do is you can take a stratum in the codomain and you can refine it into many smaller, potentially many smaller strata in the domain. And appropriately, such a map is usually called a refinement. So a refinement is a map of stratified spaces where the underlying map of topological spaces is a homeomorphism. Okay, so there's one more notion of map that I want to mention. And again, like I'm trying to get through these notions of stratifications a little bit more quickly so that we can, and if there's something that like caught your eye, we can definitely discuss this in more detail, but really I just want to mention the different things that are later on going to be relevant for the theory of transversal stratifications. So yes, the last thing I want to talk about is bundles. Namely, there's a rather straightforward generalization of the notion of fiber bundles to the stratified setting. And I'm going to call this a stratified bundle. And really what it is it's simply a fiber bundle on each stratum where, of course, fibers can now also be stratified. But really saying that it's a fiber bundle on each stratum should be actually more readable than trying to write this out. And I think it's actually pretty canonical and straightforward to write out what such a thing would be. Instead, let's just look at an example. So on the left, we have a usual fiber bundle over the circle with fiber being 2 points. And on the right, we have a stratified version. So the base space is stratified into 4 strata. And what can happen now, if you go from one stratum to another stratum, the fiber can actually change. So over this stratum, the fiber is supposed to have 2 elements. And then when we reach this point stratum, the fiber suddenly has 3 elements. And really, it's a very easy definition. Really, what you should take away is that the base space, the stratification of the base space, gives you information of where the fiber in the total space changes or can change. There's a refinement of this notion of stratified bundle, which is based on or which is necessitated by, for instance, examples coming from Morse theory, where we want to remember that fibers in the total space, that strata in the total space are actually grouped together into some bigger stratum. So for instance, maybe all of these strata that I'm marking right now are really meant to be in one bigger stratum, which would be perfectly fine bigger stratum. And this grouping together is something that we've seen already, namely in this notion of refinement. So really what we're going to look at are just spans of stratified bundles, and the other leg being a refinement. And the refinement now tells you which of the strata in the total space are being grouped together into a bigger stratum. There's another map that can be extracted from such a span. A refinement is, of course, as a map of topological spaces, a refinement is just a homomorphism. So as a map of topological spaces, the refinement does have an inverse. And composing this inverse with the stratified bundle induces a map from the right side of the span to the left side. And this map is usually not a map of stratified spaces, but it still will play a role for us. So this map, together with the span structure that defines this map is what we call a stratified parameterization. So stratified parameterization is a span of a stratified bundle and a refinement. And it should really be thought of as doing the same job as the stratified bundle. So the base space, as before, tells you when fibers can change. So when we pass between strata and the base, that's where fibers can change. But the stratified parameterization has the additional information of when strata can be glued together, can be grouped together into larger strata by this refinement map. All right. Let me also say that I omitted things from this discussion. So stratified bundles and stratified parameterizations in general can be quite badly behaved, and they're also nicer notions of these bundles, which deserve the name constructible bundle. Constructible bundles are something that I'm sure some of you are familiar with, and they can be characterized in different ways, but for those familiar with constructible bundles, I just wanted to add that really the stratified bundles and the stratified parameterizations that we're going to work with are going to be as nice as constructible bundles. But the fact that they are is actually going to follow from the situation that we look at being quite rigid. So not a lot of pathologies can arise in these situations. Okay, so this finishes what I wanted to say about stratifications. Maybe to recall briefly again, so we saw the definition, we saw entrance paths, we saw refinements, where one stratification is finer than the stratification that it maps to. And we also saw these different notions of generalized fiber bundles to the setting of stratified spaces. Yeah. Okay, so now we're getting closer to the interesting parts. And the first thing I want to discuss is transversality. So transversality in its prototypical form describes the situation where we have two submanifolds in a parent manifold. So for instance, here I've drawn the submanifolds S and the submanifold P. And transversality in the situation says that these two are in generic position with respect to each other. And usually that's expressed, or the easiest way to express this is, of course, using smooth manifolds and looking at how the tangent spaces behave at the points of intersection. Now, recalling this earlier remark I made about these higher generic paths, we could also think of this, of one of these submanifolds as a path, which generically passes through the other submanifold S. And what this tells us is how to cross the submanifold S generically in one point. And the structure that we're going to work with is going to do the same thing, but it's going to do that at all points of the stratum S. So we're really going to look at families of such generic paths which are organized in the structure of a foliation. And there are two things which I should note on this motivational example. So the first thing I've already mentioned in the very beginning. So we are not really working with general foliations. We are only going to work with standard foliations. So foliations which look exceptionally nice and which foliate Euclidean n space. So one way to think of this is as this being a local description of the foliation, but really I don't really want to say the word local too much, because how to assemble these things into something global is something that is a completely different story, and which we're not going to touch on this in this talk. But for now, let's just say we're working with standard foliations. The second point concerns us having to get the dimensions right. So really, to get meaningful transversality conditions, what you need is, for each dimension k stratum, you actually need a codimension k foliation. So for instance, in our earlier example of the stratification, where we illustrated the entrance path and the generic path, it's of course not possible to intersect a point stratum with a one leaf or a one path in a transversal way. So for a point stratum, what we need is a two leaf or a codimension two foliation of the space to get a meaningful transversality condition. Luckily for us, working with standard foliations means that all of the leaves of these foliations are actually Euclidean spaces themselves. And that means that they themselves have standard foliations. So there's actually a canonical candidate for describing this situation in a standard way, namely the standard flag foliation, is simply the foliation that you get of Rn by iteratively foliating the leaves of the standard foliation. Let me make this a little bit more precise and give an actual definition of what a leaf in this standard flag foliation is. So I define a k-leaf of the standard flag foliated model Rn inductively to be the pre-image of the k-1 leaf of the standard flag foliated model Rn-1 under the projection map from Rn to Rn-1, which forgets the last component of Rn. So that's really just nicely packaging what I was describing here into an inductive definition. Let's see how it works in an example. So over here, I'm looking at the map that forgets the last component of R3 to R2. So this would be pi less than 3. And what are the leaves, the k-leaves in R3? Well, one thing that I've not added to this definition, the zero leaves are always just points. So the zero leaves are just the points of Euclidean space. Consequently, the one leaves are pre-images of points. So the one leaves are going to be things that are being mapped to points. And similarly, the two leaves are going to be the pre-images of the one leaves in the flag foliated model of R2. And this really gives a nice way of not only describing the leaves of this foliation, but also thinking about what parameters do you need to describe these leaves. So for instance, the one leaves, how many one leaves are there in R3? Well, the number of one leaves is essentially parameterized by all the points in R2. And in this sense, you can think of this giving a parameterization of, or space of parameters for all the leaves in R3. There's also a notion of maps that these standard flag foliated models have. It's very similar to standard flag foliations of Rn. So for standard flag foliation, you want the map to preserve the leaves of the foliation. So you map leaves of the foliation into leaves of the foliation. And very similarly, a flag foliated map of Rn to Rn is simply a map which maps k leaves for all k into k-leaves of the codomain. And we're going to see an example of such a map in a moment. Let's remember why we were talking about this transversality of this flag-foliated standard foliation in the first place. Namely, really we wanted to impose meaningful transversality conditions for all strata of stratification. So let's get to that now. So what we want is for every stratum in the stratification, we wanted to intersect transversally all the leaves of the flag-foliated standard model. And the first question that one needs to consider when one tries to make this precise is, do we really need smooth structure to describe these transversal intersections? That would be a little bit, well, not annoying, but it would be cumbersome because I've not introduced anything smooth so far. So it would be bad to now get back to stratifications and try to do everything in a smooth world. In fact, you do not need smooth structure because really you can use this flag foliation and the notion of flag foliated maps to define neighborhoods in which things can be straightened out. So for instance, I try to illustrate here an embedding of a one manifold in R2, which is not a smooth embedding, so it has this little kink. But even if there's this little kink, there's gonna be a flag foliated map from a stratification where this thing looks completely straight into a neighborhood of this thing. So it's gonna look something like this. So here we have what I called a completely straight stratification of flag foliated space, and the stratum is transversal to all the leaves. And there's an FF map of this thing into a neighborhood of this kink. And let me say what I mean by. So someone turned on their microphone.
Hey, Christoph, this is Aaron. Yeah.
Yeah.
So I guess two questions. So the flag foliated model, I guess, what exactly is the data? Is it like a flag of foliations of different codimensions that are just kind of all keeping track of what you might want to model locally later?
Yeah, I mean, actually the data is just an order on the components of the product of Rn. Really, I just wanted to introduce the notion of leaves. So when I refer to leaf, I refer to a certain subspace of Rn, but the data that determines the subspace is just ordering the components, because the only thing you need to know is what the last component is when you project out. Mm-hmm. So that is really the only data of the standard model.
Okay. And then regarding this question about C-infinity structures, are you making an assertion along the lines that a map preserving foliations between RNs is necessarily smooth or something like that? Or is there anything like that embedded in this?
No. Really, I'm just defining a notion of transversality. I'm not taking the smooth notion of transversality and trying to replicate it. I'm saying that there's a meaningful notion of transversality, which is actually something that you know. It's just conicality in disguise, and yes, I was trying to motivate that it's meaningful by drawing a picture where it's completely evident that something is transversal, and telling you that there's an embedding. So this is generally isomorphic to a neighborhood of this kink. So
okay, and here isomorphic means homeomorphic is the point. More maybe homeomorphic plus stratification.
Yeah, homeomorphic plus stratification. So it's an isomorphism of stratification. The underlying map is flag foliated.
Gotcha.
Exactly. Yeah.
Okay, thank you.
Yes. So I was just about to tell you what I mean by this being a straight line intersecting these leaves of the foliation transversally. Really, what I mean by this is that it's a product. It's a product of just R, so just the straight line with flag foliation, however, with something that is a cone. And as I mentioned 15 seconds ago, this is something that will look familiar to people that know conical stratifications. It's really a very frequently imposed condition on stratified spaces. But if we use this conicality in conjunction with a flag foliated structure, what we get is something that looks like this transversality condition. So really, the moral of the story is that instead of working with C-infinity structures, we're just going to impose this conicality condition instead, and this is going to define what we mean by transversal. Let me say a little bit more about these cones. So I just want to illustrate these by example. So I'm calling such a product a flag foliated conical neighborhood. So such a product of something that looks like a cone with a stratified cone point and a Euclidean space. And I also wanted to interact with the flag foliated structure in a reasonable way. Essentially in a reasonable way such that all the pictures that you would draw as a result actually look like C-infinity transversality. So for instance, what we can take is we can take the product of the real line with the cone of S1 flag foliated. So this is now an R2 with a cone point. If we take this product, the result looks like a one stratum which transversally intersects all the two leaves of flag foliated 3 space. Similarly, we can take the product of 2 space and 1 space, where the 1 space again has a cone point, and what we get is well, a 2-dimensional stratum, since we multiplied the cone point with something 2-dimensional, and this 2-dimensional stratum now intersects all the 1 leaves transversally. And what we're going to impose on our transversal stratifications is that all the strata have neighborhoods which are conical, so have neighborhoods which are of these forms. But in fact, that's not the entire story yet. So conicality is not all we need. We also need something that I would call inductive transversality. And this really has to do with this inductive structure of leaves in the standard flag foliated model. And it's best explained with an example. So let's look at some stratifications. So here in this very first picture, I've drawn 2 one-dimensional strata, which clearly transversely intersect all the 2 sheets because they all have neighborhoods of this form, which flag foliatingly embed into the stratification. And what I want to do is I want to start deforming these lines. I want to start bulging them out in opposing directions such that suddenly at one point in time, they actually intersect the same 1 leaf. So now they intersect the same 1 leaf. And then if you transform them, if you deform them even further, they will eventually look something like this. And now they will intersect actually at 2 1 leaves, or there will be 2 1 leaves which both of these lines intersect. that's an absolutely generic situation, and it's in fact an example of a transversal stratifications, but let's look at an example which is not as generic. So let's start with the same stratification. So two lines intersecting transversally all the two sheets, and what we're going to do is we're going to move them in the same direction, but we're going to move them in a way that suddenly they don't intersect just a single one leaf, but they start to mutually intersect a continuum of one leaves. So now they're intersecting this entire interval of one leaves at the same time. And then we just transform them even further. And again, they're going to look like the end stratification of the first case. So our gut feeling tells us that generically such a thing will never happen. But really, we want to formalize this gut feeling. And this is where the inductive structure of the setup comes into place. So let's remember that what I've drawn here, so really we're working in R4, and what I've drawn are the three leaves of R4. So I've drawn four-dimensional space, and this thing is a three-dimensional leaf of R4, and as a three leaf, it's the pre-image of a two leaf of R3. So I've drawn the corresponding mappings to the two leaves, and I've also drawn the projections of the strata into these leaves. Now, the setup is so simple that I can actually say I've drawn the projection of the strata. In general, saying I'm projecting strata is not a feasible thing. So really, this is where our earlier notion of stratified parameterization comes in. Really, when I say projected strata, I mean that this map is a stratified parameterization in the sense that these strata and the base, they record exactly when the fiber changes. So for instance, over this point, the fiber is actually just the trivially stratified one leaf. But over this point here, it's the one leaf with two strata on it. So really, when we go from this stratum to this stratum, the fiber changes. So I'm saying projected strata, and you can think of these being projections, but really formally we're working with stratified parameterizations at this point. And what I'm telling you is that this stratified parameterization can detect that this situation that I've drawn here is really non-generic. So it's really something that can not happen generically. And the way that it detects this is by just using what we've done before, namely just by a violation of transversality. So this stratum, which appears suddenly here, can actually not have a neighborhood of the required conical form. So transversality definitely has to fail at this point, which is in fact independent of the base stratification that you choose. In general, for a stratified parameterization, you can choose different base stratifications. But whatever such base stratifications you choose, at this point, the transversality condition will be violated. So the moral of the story really is that we can detect certain non-generic situations by looking at what happens one inductive level down. And these two things, so the conicality together with the inductive conicality, are everything we need to define n-transversal stratifications. So let's do that. I'm just going to show the definition, and we will go through it in detail. So an n-transversal stratification, well, is the stratification of Rn such that firstly, we have this conicality condition that we spoke about. So for all points, there is actually an appropriate flag foliated conical neighborhood. And it also makes complete sense to require that the cone that is involved in this conical neighborhood should be inductively transversal itself. But let's just say this is the conicality condition that we talked about earlier. And then the second point is really this inductive transversality that we talked about, which is that an n-1 transversal stratification G exists. So this is the stratification now on Rn-1. And the map that forgets the last component of Rn from F to G is required to be a stratified parameterization. And again, there's a technical condition that this bundle should be proper in a specific sense. But we can absolutely completely ignore that for now. So maps of these transversal stratifications are straightforward to define. A map is simply a map of stratifications which preserves the flag foliation structure of the standard flag foliated model. And the only thing that we're going to use is a notion of isomorphism that results from this definition of maps. And I'm going to illustrate that notion of isomorphism with an example. So here are some transversal stratifications, actually the ones which I've already mentioned in the very beginning. So let's start on the left. So this is the Cusp Singularity, which I talked about earlier from singularity theory. And what happens, or the theory of dualizability, what happens is that it can be nicely interpreted as a transversal stratification such that the critical points of the usual setting from singularity theory become one strata, and the critical point where the differential is actually degenerate becomes a zero stratum. Very similarly, the pair of pens becomes a stratified an transversal stratification where the seams of the pens become one strata and the saddle point in the middle becomes a zero stratum. Just to give an idea of what the notion of isomorphism can do. So really an isomorphism can squeeze or reparameterize the leaves, the k-1 leaves, within each k-leaf, less arbitrarily, up to the map, of course, being continuous. So for instance, what we can do is we can take this one leaf here, and well, there are going to be loads of zero leaves inside this one leaf. And what we can do is we can just shift them together a little bit or shift them around. So this is what happened when, for instance, going from this picture here to this picture on, so from going from the left to the right, we're shifting around these zero leaves a little bit. But this is an isomorphism of this transversal stratification. All right, let's get to maybe the most interesting part, namely the fact that these transversal stratifications actually have an underlying algebraic or combinatorial framework. I want to start with a suggestive remark, namely
Christoph, this is David. Yep. I'm sorry if you let me know if the lawnmower near me is too distracting. No. Before we move on to the next section, could you say a word on the regularity around as strata meet into deeper strata? So specifically, like for instance, you mentioned that I would say you're not demanding C infinity, that sense of regularity stratum-wise. But is there any kind of regularity of links or anything like that around strata that you're demanding, or does that regularity somehow follow through smoothing theory or something?
So the regularity in a way follows inductively. So because you you require the cones to inductively satisfy the definition, and everything in this definition is also something that I've not mentioned explicitly, is everything is assumed to be finite. So all stratifications are finite, and that means that, for instance, everything is going to be PL. So we're in fact going to see that this finite combinatorics that corresponds to these transversal stratifications has a geometric realization. And ultimately, these links look like the geometric realization of some finite posets. So in that sense, they're regular.
Okay. So, okay, thanks. So the regularity might follow from smoothing theory, that sounds like.
Yeah, that, yeah, that as well, yeah. Okay, so let's get back to the suggestive remark. Namely, we had this inductive condition over here in the definition, which was asking for the existence of a stratified parameterization of Rn, of a stratification of Rn over Rn minus 1. But then the stratification of Rn minus 1 will, of course, inductively satisfy the same definition. So really what you get is you get this tower, or this chain of stratified parameterizations. And I want to ask what happens if we replace stratified parameterizations by the simpler notion of stratified bundle. And we'll just work through it in an example. So it's really something really simple. Let's work backwards. So let's start with what can happen in R0. Well, in R0, there's just one stratification, which is the point. And how does a finite stratification of R1 living over R0 look like? Well, it looks like a couple of zero strata stratifying the real line. In the next step, what we have to do is we have to essentially do the same thing, but over each stratum. So each stratum is now going to have a fiber, which is one-dimensional. So again, it's going to be just the real line with some zero strata in it. And the entire fiber over the stratum is just going to look like a trivial product of this this line this line as stratified by a zero stratum or by several zero strata. This is because inductively all of these stratifications are actually, all of these strata are actually disks. So really nothing interesting can happen. In each case, the fiber needs to be aligned with zero strata on it, and the stratified bundle then guarantees that it looks the same over the entire stratum in the base, which inductively is a disk. This is also why it's called disk stratification. So let's just formally write down the definition. A disk stratification F is a length n chain of stratified bundles where the kth component of this chain is simply the projection map from Rk to Rk minus 1, and we have some stratifications on these Euclidean spaces. So yes, the result of this definition should be really imagined as these very easy stratifications of Rn where everything is a disk. And I want to make two core claims about this notion of stratification. Namely, the first one is every n-transversal stratification has a refinement by an n-disk stratification. So that uses this previous notion of refinement. So every n-transversal stratification, like the one on the left, can be made finer, and this finer stratification is then actually an n-disk stratification. And in fact, so the core claim continues. There's this version of the Hauptvermutung that I mentioned in the very beginning, independent on how bad this transversal stratification looks like in arbitrary high dimension, there always exists a unique minimal disk refinement for any transversal stratification. And minimal here means with respect to refinement. So there's a disk stratification which is going to be coarser than any other disk stratification, and this disk stratification is unique. The second claim concerns now the combinatorics. So the second claim is that the disk stratifications can actually be reconstructed up to isomorphism from their entrance path poset chain. And by chain, I really mean the entrance path poset, but applied to this entire chain of stratified bundles. Because of course, we earlier saw that the entrance path, that a map of stratification descends to a map of entrance path. And in this sense, the entrance path poset is also a functor from stratifications to posets. So we're going to apply this entrance path construction to the entire chain that defines an endless stratification. And let's do this in an example. So here's a part of a chain defining a disk stratification, a very simple part. And in the bottom, I've drawn the corresponding thing that happens on entrance paths. And I want to make a couple of observations about what happens at the level of entrance paths. The first thing is that, well, there's a combinatorial structure that reappears in these pictures, maybe the entrance path of just a one-dimensional disk stratification. So this, for instance, appears as the fibers of this map as well, because the fibers in the disk stratifications are also just one-dimensional. And this is called a singular interval. So a singular interval is a poset that is obtained as the entrance path poset of a one-dimensional disk stratification. So simply of a sort of stratification of R1 with finite zero-dimensional strata. And let's make a couple of observations about this map. Let's call it F. Well, I've already mentioned that the fibers of F are singular intervals. So they're of this form defining singular intervals. Something a little bit less trivial is the following interesting observation. So the arrows that can happen in between fibers, so when you pass from one stratum to another stratum in the base, then the arrows that happen in between behave in a certain functional and simultaneously co-functional way. So first of all, let me call an object of a singular interval zero-dimensional if it corresponds to a zero-dimensional object in the disk stratification, and let me call it one-dimensional. Let me call it one-dimensional if it corresponds to a one-dimensional object in the disk stratifications. Then the claim is that maps obtained in this way actually map the zero-dimensional objects functionally and the one-dimensional objects co-functionally. And by this, I mean the following. Let me use some colors. So whenever you have an arrow in the base, then in the direction of this arrow, the maximal objects are going to have arrows that associate the zero-dimensional objects are going to have arrows that associate the zero-dimensional objects of one fiber functionally with the zero-dimensional objects of the other fiber. So that's a functional dependency in the direction of the arrows in the base. And conversely, the one-dimensional objects have a functional association, but in the opposite direction. So let's mark the one-dimensional objects in these fibers. So these are now mapped functionally, but in the opposite direction of the arrow in the base. So let me try to draw arrows. So these are arrows of the co-functional association. So that's the first core property of such map. There's also a second core property, which is simply stated as that no lines will ever cross. So there will never be a case where I have to draw two arrows with a crossing. So I can always draw them in a way that they don't cross in the plane. And of course, you can make this a little bit more formal, but really just wanted to mention that there is this combinatorial characterization of these maps, and consequently define a singular interval bundle to be simply a map of posets which satisfies these three things. So which satisfies that fibers are singular intervals, which satisfies the functionality, co-functionality, and which satisfies that no lines can cross. And this leads to the following definition, which mirrors the definition of singular of endless stratifications, namely a singular cube generalizing from what was a singular interval is a chain of such singular interval bundles of poset maps, which are singular interval bundles, which ends in the terminal poset. And there's also a notion of maps, which in fact is simply chain maps. And you can use these chain maps to define meaningfully when something is, for instance, an embedding or certainly an isomorphism. Now, the claim is that endless stratifications, in fact, the topological category of endless stratifications is as a topological category equivalent to the one category of singular cubes and their embeddings, actually. So we're working with embeddings. And the way this goes is really what I've started this core claim with. It goes by taking entrance paths, by applying the entrance path construction to the entire chain that defines an endless stratification. All right. Let me indulge in one quick remark, which is kind of an aside, but it's important for actually working out the combinatorial part of the story. So you can easily just vary the space poset to be something else. You can just vary it to be, for instance, the K-simplex. And this defines a simplicial set of these singular cubes, which turns out to be something which is much simpler than a simplicial set, namely it's actually the nerve of a category Si. This has to do with the fact that really the simplices in these singular cubes are extremely highly ordered. So actually there are multiple orders on these things, and I try to just artistically give an idea of where this highly orderedness comes from. But yeah, this category Si is not going to play a role here. It plays a very important role for actually developing the theory of these combinatorial singular cubes. Okay, let's remember why we actually went on to this, this path of endless stratifications. Namely, really, we want to classify transversal stratifications. And the way we're going to do that is by just mimicking. So just as the singular cubes mimic endless stratifications using this entrance path construction, we're going to mimic all the tools, all the topological tools and stratification tools that we use to define transversal stratifications on the side of the entrance path poset. So I'm going to draw a little table where on one hand, I will have the topological notion from stratified topology, and on the other hand, I have what happens at the level of entrance path posets. So the first thing which we need is refinements. Like refinements play a crucial role in in our strategy to classify transversal stratifications, because we said that n-disk refinements or each transversal stratification has this unique minimal n-disk refinement. And what a refinement is at the level of entrance path posets, so really this xn is now supposed to be the entrance path poset of the disk stratification. At the level of entrance path posets, a refinement is a quotient map with connected preimages. So what we're going to do is we're going to simply augment the definition of singular cubes, and we're going to, in addition to this chain of maps up here, we're going to also put another map on the xn into some poset p, and this is later on supposed to model what this refinement is doing. So really, let me call the resulting thing a stratified cube. So a stratified cube is going to be such a chain together with a map on the total poset xn to another poset, which is a quotient map with connected preimages. All right, so refinements are these certain quotient maps. We also use products. In fact, we use very trivial products. We use products with Rn. And at the level of entrance path posets for disk stratifications, what this is, it's really just a trivial chain extension, an n-fold trivial chain extension of the base poset with more trivial maps of the terminal poset. And yeah, I'm just going to mention these things to give an idea of the translation from topology into the entrance path poset world actually being a thing. But of course, I'm omitting a detailed discussion at this point. We also used neighborhoods, arbitrary small neighborhoods, and to define this notion of transversality. And arbitrary small neighborhoods around a stratum translate to overpost sets, which is somewhat straightforward to see, because if a stratum is still part of an arbitrary small neighborhood of another stratum, then there will be eventually an entrance path going from the first stratum into the stratum which you take the neighborhood of. And this entrance path simply translates into an arrow in the overpost set. Okay, we're almost done. One thing that's really important to mention is we also freely work with the notion of things being isomorphic in the context of stratified stratifications of Rn and transversal stratifications. And this notion of isomorphism, which relates to this first point where we defined stratified cubes, requires technology, and this is a combinatorial version of this Hauptvermutung which I mentioned earlier. And then you can also use this Hauptvermutung for the very last point, namely stratified parameterizations. This now simply becomes an exercise to really mirror this inductive definition at the level of the combinatorics and use this combinatorial Hauptvermutung to check for local triviality, which is used in the definition of these stratified parameterizations. If you assemble all of these things together, you actually get a definition of transversal singular n-cube. So it's like the combinatorial analog of transversal stratifications. And the theorem that results from putting all pieces of the puzzle together is that there is, in fact, a bijection. So this is a bijection of set from the isomorphism classes of n-transversal stratifications to transversal n-cubes, but not any transversal n-cubes, but the minimal representatives of transversal n-cubes with respect to this combinatorial Hauptvermutung. And really how this works is as illustrated in the very beginning. So you take your transversal stratification, you refine it to the disk stratification. In fact, you use the minimal refinement, which is guaranteed by the Hauptvermutung. And then this is a chain of things so you apply the entrance path posset to this chain, you get a singular cube, S. And now you use this early observation about refinements being maps to equip the singular cube. So we take the singular cube as, let me do this a different way. So we take the singular cube and equip it with a map on its poset as n into the entrance path poset of T. And the resulting thing is going to be the image point, the image of T on this other side. So the isomorphism class of T will then be mapped to this transversal singular cube on the other side of the theorem. And there, well, there are several things that you can do now, because what this theorem enables you to do is you can work with these geometric structures of n-transversal stratifications in a combinatorial way, or you can work dually in this geometric and combinatorial from these geometric and combinatorial perspectives. And one application that I wanted to discuss are tangles. But I think just to illustrate this theorem a little bit more, I wanted to briefly show some pictures of these minimal disk refinements of transversal stratifications that you probably know. So let me show these pictures. So this is also about the claim that the framework works for higher dimensions, because all the things I've drawn were really low dimensional so far. So let me give you some higher dimensional examples. So I hope this is more or less visible. But so on the left, what I'm showing here is a transversal stratification. In fact, a transversal stratification of a flag-related model of R4. And then on the right, I'm going to give its minimal disk refinement, which then can be translated into the combinatorial structure by taking this chain of things and mapping it into the entrance path poset world. So this first example is, for instance, the four-dimensional picture that you get from drawing either the Young-Beck-Sterata or the third Reidemeister move. So what this is it's three braids assembled together on three strands, and a deformation of these braids into a different way of assembling three braids onto three strands. And I'm sure most of the audience is familiar with that, but the minimal disk refinement is something that I think looks quite nice. I mean, it's something four-dimensional, so it also looks quite big. But for instance, what you see nicely at this level of the two-dimensional space is really that the story that happens is that you take these three braids, you merge them into one braid, and then they get unmerged into three braids, which are in a different constellation, which, however, is information that only lies in the higher dimensional spaces. Just as a second example, I've mentioned the cusp. There are other singularities. Actually, all singularities from singularity theory can be translated into transversal stratifications. So this one here is the swallowtail, which takes two of these cusps and interleaves them in a certain way. And then it trivializes this interleaving of the snakes, which causes there to be at some point a zero stratum, and then eventually we end with just the identity. And again, this has a minimal disk stratification, and what I think is nice to remark about this minimal disk stratification is that at the level of R3, so at the three-dimensional level, you really recover the classical picture of the singular locus of the singularity, of the swallowtail singularity. And as a final example of a minimal disk stratifications, something that is even higher dimensional, so this is something 5-dimensional. So this is about the braid in codimension 2 being the same, so the overbraid in codimension 2 is the same as the underbraid. And this again can be expressed with this transversal stratification, and I think I'm going to get back to the talk in a second, but the minimal disk refinement has a nice R3, which looks which tells you about what really happens at the points in the middle of the braid, actually. Okay, but this is more of a extended set of examples to demonstrate how this works in higher dimensions. All right, so I don't have a lot of time. Let me give the main idea. An n-transversal M-tangle is simply an n-transversal stratification such that the union of all codimension non-zero strata is an M-manifold. So really it's an n-transversal stratification where when you take the union of all stratifications which are not codimension 0, you get an M-manifold. So for instance, the following is a tangle or a transversal tangle. It's of course something that you've also seen many times. The double braid can be made into a transversal tangle, and this thing is also something that illustrates a transversal tangle. And the idea of stratifying the space is really by defining a notion of perturbation and then using the combinatorics to decide when a perturbation makes things genuinely simpler or when a perturbation actually has things, it perturbs something into things which are of the same complexity. So yeah, let me go through this with a little bit more detail. A perturbation is, in an appropriate sense, a tangle bundle over one simplex. So by the one simplex, I really mean the stratified interval with the endpoint being stratified, and all of this can be expressed combinatorially. Here are some examples. So this is a tangle perturbation. You take the cup and you perturb it into a sequence of 3 cups. Here's another perturbation. So for instance, you can stack together 2 saddles. So these are supposed to be saddles. And you can form, in an appropriate precise sense, a bundle over the one simplex, which converges these two saddles further and further together until they actually touch a point. And the resulting thing is usually called the monkey saddle. And what I want to argue is that these 2 examples have very different quality. So in this example, you take the cup and you just re-express it in cups and caps, whereas in this example here, you take something which is highly degenerate, which is somewhat degenerate in multiple directions, and you express it in something which is less degenerate. And this notion of something being simpler or less simple can be very easily, so first of all, everything I've said so far can be written down as an algebraic or combinatorial definition. But things being less complex or more complex can now be expressed simply by looking at the combinatorial classification and looking at how complex this combinatorial classification is. And this allows us to actually say when a perturbation is simplifying. And then we say that a transversal tangle is of codimension k if the longest chain of simplifying perturbations ending in this tangle is of length k. So if there's a transversal tangle and we have a chain of length k of simplifying perturbations, then it's at least in codimension k. Let's look at codimension 0 strata of three-dimensional, three transversal 2 tangles. Well, these are pictures which hopefully look very familiar. So it's, for instance, the saddle, it's the birth of the circle, and it's the cusp. And I mean, this should remind you, for instance, of generating sets for certain forms of cobordisms. And really, in this vein, I want to end with the following conjecture. So codimension 0 and transversal n minus k singularities. So n minus k tangle singularities are those tangles which actually are cones. So they have a single cone point. Form up to isomorphism in the topological world, up to isomorphism, in the combinatorial world, literally there's nothing that needs to be done, form a finite set. And what you can think of as the saying or this hoping is that the simplest codimension 0 tangles actually form a set of generators, a finite set of generators for all n transversal n minus k tangles. Okay, yeah, that's it. Thank you very much.
Fabulous. Are there questions for Christoph?
Hey, Christoph, this is David Ayala. I have a couple of questions. Maybe I'll ask the first and see where it goes. I guess I have a technical question and a general question. As far as the first theorem that you mentioned, I was wondering if you believe that could be upgraded to maybe groupoids instead of isomorphism classes. And to that matter, if you know, the earlier theorem.
Even earlier?
There we go, right there.
Okay.
Where'd it go? Yep, right there. Yeah, so that's a statement about isomorphism classes of something. And I was wondering if you have thoughts about the groupoid, potentially interesting, of n transversal stratifications. And for that matter, if there are any non-trivial isomorphisms.
Yes, yeah. So I agree that it's somewhat unexpected that this is not an equivalence of categories. And well, let me first say it's not a bad thing that it's not an equivalence of categories, because really the point of the narrative to some extent was that everything you can do topologically, you can like copy over and do combinatorially, and it goes both ways, more or less. But really, an issue with upgrading this to categorical equivalence is that the right-hand side is somewhat reluctant to having a good notion of maps. So it's
yeah, I was even wondering about just isomorphisms. So not a categorical equivalence necessarily, but just on underlying groupoids or something like that.
Yeah, I mean, yes, on underlying groupoids, it is true. So the underlying groupoid on the left-hand side is going to be actually equivalent to the discrete set on the right, because there are no
no non-trivial isomorphisms. Okay,
exactly.
Gotcha.
Yeah.
Is that maybe the most naive definition of morphism doesn't work, but have you also thought about concordances as a way of introducing maps on the right-hand side?
I've not thought about it, but I'm sure. Yeah, I'm sure something like this would actually work. Yeah. Yeah, similar to what I've very briefly mentioning about bundles over the interval and so on. Yeah.
Maybe I can ask, this is David Ayala again. Maybe I can ask the more technical question, which is what the notion of constructible bundle is that you're using. I wrote a paper on that, and
yes, yeah.
and essential in that definition is a notion of links. And to me, it seems like there is no notion of links in this theory. So that's where I ask.
Yeah. So I can give you a very indirect characterization of what a constructible bundle is. So in this world of stratifications that I've mentioned so far, constructible bundles are the maximal class inside stratified bundles. Sorry. Such that, first of all, constructible bundles compose with stratified bundles to give stratified bundles. And secondly, constructible bundles are closed under pullback by open maps. Now, I don't really think that's an answer to your question, but really what we want is that, yes, the definition does not use, so a more explicit definition would require that if you have a bundle X to some base space B, and you have an open refinement, which is of the form of some stratified space. So I hope I'm reproducing that correctly. So you have an open map, which is possibly a refinement, and the the domain of this map is of this product form stratified space times some open set. Then for each X in U, there exists an even smaller neighborhood V in U, such that the pullback gives something trivial. Sorry. So this is of the form F times identity. So it's a very weak notion of constructible bundle, if you want. But honestly, I think the structures that we work with satisfy stronger notions of constructible bundle as well.
So is there a reference that you're using, or is it your own notion?
This is a notion which works well with just the definitions of stratified bundles. Yeah. So
your own
there's no
notion.
reference. Yes.
Okay.
Yeah.
Gotcha. Thanks.
Yeah.
Hey, this is Aaron again. I was wondering what goes into the proof of the Hauptvermutung in this situation?
I think that's a great question. I mean, all questions were great, but I'm particularly enthusiastic about this question. So really, you never prove the topological Hauptvermutung directly. You only prove it very indirectly by proving the combinatorial thing. The combinatorial thing can be rephrased as saying that so this category of singular cubes, which is equivalent to endless stratifications, if you restrict this category to only contain refinements, so now it's a map of singular cubes, which only has refinements. And in fact, I want to use this augmented notion of singular cubes where maps, where these chains are also augmented with some map into a poset P. So I have my chain. of singular interval bundles, and I have this augmentation with a map to a poset P, and then the combinatorial Hauptvermutung tells you that the overcategory of this category of singular cubes, only with refinements and with a labeling in some poset. And if you take an object of these things, look at the overcategory, has a unique terminal object. So
it's actually premised on that isomorphism. You have to prove that one first.
Exactly. Yeah, exactly. Yeah.
Okay.
Yeah. So the main work really goes into this combinatorics, and the reason why I'm so enthusiastic about this is because it's a quite general result. For instance, instead of a poset P, you can do the same thing with a quasi-category actually, and then it would be unique up to contractible choice. But I think it's a nice result, and going into the technicalities of this combinatorial result is probably going to take more time.
Oh, that's fine. This is the sort of answer I was hoping for. And I guess this is like an instance of the general paradigm of the connection between topology and algebra in the first place.
Yeah, I agree.
Cool, thank you.
Maybe this is a good moment to transition to the tea room for anyone who feels like joining us there. I just put the link in the chat, in the Zoom chat. And yeah, thanks again, Christoph, and we'll see you in the tea room.
Thanks again, Christoph.
Thank you.